Onu düzeltin. Okay. Look at the correction. Okay. That's Fermi-Dirac. Because in the logarithm we have 1 plus. We have to carry that 1 plus, okay? So towards the end of the lecture, we tend to make mistakes then. And you are not saying anything. It's bothering me. Okay, let's look at the bosons. Bose-Einstein case. For bosons, this ground potential, remember, if we divide this by kBt, we have the Q potential, isn't it? So this is ground potential, omega, kBt to the power nk. Now this is a power series, isn't it? Nk can be anything. Doesn't have only two values, as in the case of Fermi-Dirac distribution function. So what is the result of this sum? X, onu öğrendik artık. Now you have minus sign coming in, okay? So if you consider the average number of particles in state K, then PV K then mu, this is going to be very simply minus kBt over 1 minus e to the minus beta ek minus mu, logarithm 1 over the function and derivative of the function minus beta e to the minus beta ek minus mu. kBt again is going to be cancelled by beta. So if you take into parentheses, you have 1 over e to the beta ek minus mu minus 1 for Bose-Einstein case. So you never say what is the importance of a plus or minus. It is extremely important. That plus and minus difference is the difference between fermions and bosons. Okay? The classical case, the classical particles obey Maxwell-Boltzmann distribution, and it is when the exponent is quite large, classical particles, when this beta times ek minus mu is large, in both cases, this 1 doesn't have any meaning anymore. Plus 1 or minus 1. 1 is very small compared to a very large number, isn't it? So you can omit that. The difference between fermions, bosons disappears. You have the following thing, beta ek minus mu. This is Maxwell-Boltzmann distribution. For classical particles. Okay? If you plot these three things, average occupation numbers for classical fermionic and bosonic systems, you have the following important difference. Here is beta, or 1 over kBt, E minus mu over kBt, exponent. Here is the average occupation number, average number of particles per state. Here is 1/2. Here is 1. That's 0. You have the following picture. For what is this? Which particles have this property? When that becomes big, it must be Fermi-Dirac, isn't it? It goes to 0. And when it is becoming 0, 1 over e to the 0 plus 1 is 1 over 2, isn't it? 1 plus 1. So that's Fermi-Dirac distribution function. Well, one more property, let me show you. If something is going like that, blowing up as that thing goes to 0 is what? Bose-Einstein, because minus 1 minus 1 is 0. 1 over 0 is infinity. So that's Bose-Einstein. Oh, that means you can put lots of particles into the ground state when temperature is low enough, isn't it? That's Bose-Einstein condensation. For the classical case, Maxwell-Boltzmann case, you have something like this, simply because you have an exponential. If the exponent is 0, you have 1, isn't it? Exponent is 0, you have 1. So that's the Maxwell-Boltzmann case. Now, we need a physical understanding of what the particles are doing. Are there any correlation between their positions? There must be, isn't it? It's purely coming from the fact that they are quantum particles, bosons and fermions will behave differently. How are we going to study that? By calculating the density matrix. What is the probability of having a particle at R1 and another at R2? That density matrix is going to tell us how they are going to behave, physically, I mean. So, density matrix, we want to understand what is the correlation between their positions? Are there any correlations at all? Of course, there must be. Density matrix gives us that probability. Well, let's calculate this. Which is proportional to, or is the probability that one particle is at R1 and the other particle is at R2. Isn't it? What is this probability? That's an important question, I think. I'm not going to do the full calculation, but I will give you the pages of my calculation. You can check my calculation. Okay? So here is the way you write it. Eigenstates. You need that. There's R1, R2. Symmetrized plane wave states in terms of plane wave states. Here is the plus or minus 1 e to the I k 1 dot R2 plus K2 dot R1 divided by square root 2 factorial square root V square. Plus is Bose-Einstein, minus is Fermi-Dirac, isn't it? So Bose-Einstein is up for positive sign, Fermi-Dirac is down for negative sign. When we interchange them, we have to have a negative sign for Fermi-Dirac. Okay. So if you want to write this probability, then matrix element of the density matrix, you have the following calculation. As I told you, I'm going to give you the calculation. It is going to be okay, let me give you the calculation at the end of the lecture. Let me write the result for this. that density matrix comes out to be, or the probability comes out to be 1 over v squared, 1 plus or minus, plus for Bose-Einstein, minus for Fermi-Dirac, e to the minus 2 pi r12 squared lambda t squared. So it is Bose-Einstein up, Fermi-Dirac down for the signs. Okay? What does that mean? This is the probability of finding one particle at R1, the second particle is at R2. Okay? Classically, you don't have this term. You have 1 over v squared. Okay? So this term tells us about the correlation between positions. Coming solely from the fact that these particles are bosons or fermions. Okay? So, if the distance between particles, this is R12, R2 minus R1, okay, the distance between particles, if this is of the order of lambda t, the thermal wavelength, you know quantum effects dominate at that limit, then there is a difference from the classical result, the maximum difference from the classical result. Otherwise, that correction may be small. Now, let's look at that factor as the distance between them is large. Let's look at that factor a little bit closely and understand the behavior of bosons and fermions. Pair of bosons, if we are dealing with them, it's 1 plus e to the minus 2 pi r squared, distance between particles, divided by lambda t squared, goes to where? As r goes to 0, it goes to 2, isn't it? Probability is larger than the classical one by that factor. They like to get close to each other. Let's look at the pair of fermions. One minus e to the minus 2 pi r squared divided by lambda t squared. This goes to 0 as r goes to 0. Isn't it? 1 minus 1. Huh? So probability being 0 means they don't like to get close to each other. They don't like each other, in other words. They are not social things. Bosons are opposite. They are social. They like to be together, isn't it? Is this Turkish character? They don't like to get close to each other. So, fermions have negative correlation, and bosons have positive correlation. Okay? That's important. let's write this in terms of an effective potential energy between particles coming from their fermionic or bosonic character. Okay? Let's transform this into interactions between particles. I will give you this calculation, so don't worry. Let's define a statistical interparticle potential. Let's call that V statistical R. Okay? This must be such that the Boltzmann factor is equal to pair distribution function. That means when you take logarithm of both things, you have to have minus beta VSR is exactly equal to logarithm 1 plus minus e⁻³ minus 2 pi r squared over lambda t squared. Again, plus for Bose-Einstein, minus for Fermi-Dirac particles. So the potential is then that we have to understand 1 over kBt minus kBt times the logarithm. We know as a function of distance between particles, this effective potential between particles. If we plot this function, we see the following. As a function of distance between particles, beta statistical potential R over kBt here is 0.5, here is 1, something like this. Fermi-Dirac minus ln2. For the Bose-Einstein case, it is negative. What is the meaning of negative potential energy? It is attractive, isn't it? So negative means attractive. Positive means repulsive. So fermions repel each other effectively. They don't like to be in the same state. Remember the Pauli exclusion principle. But bosons effectively attract each other. They want to be together. They can be in the same state in large numbers. Okay? That's the important difference between the two. So a statistical attraction between bosons, a statistical repulsion between fermions. Extremely important. Well, something is going to zero when the factor is going to zero. What does that mean? Can you interpret this zero? When R becomes large or temperature becomes small, there is an important, when R becomes large, temperature becomes high, this difference is disappearing between fermions and bosons. That means in the classical limit, there's no distinction between fermions and bosons. At high temperatures, you cannot see any difference. To see the real difference between fermions and bosons, you have to lower the temperature. Okay? I think that clarifies the role of fermions and bosons, isn't it? It is quite clear how do they behave as quantum particles. Do you have any questions about them? Do you understand now the meaning of Maxwell-Boltzmann distribution function, Fermi-Dirac and Bose-Einstein distribution function? You should understand this. Look, those forms of those functions tell you something about the behavior of particles. When you put them together, some are avoiding each other, some are getting together. Extremely important. Of course, later on when we study them separately, we are going to study them separately. We are going to look at Fermi-Dirac systems, look at Bose-Einstein systems to finish our discussion of non-interacting particles, and then we are going to introduce the interactions between particles. But we are going to see that bosons would like to go into the same state. If the number of bosons in the ground state becomes large, you have Bose-Einstein condensation. Come together in the same state. Never observable in a fermionic system, isn't it? No condensation. Their distribution is totally different, and this determines the physics. Extremely important, you see? When we study fermions separately and bosons, you'll see what that means in terms of pressure of the gas. We are going to see that this will cause an outward pressure for the fermionic case, electrons. In stars, that will be the pressure against the gravitational collapse, so that may give rise to a stable star. Extremely important, isn't it? It determines the physics of the system to the fullest. We are going to see them when we study these systems separately to finish the discussion of interacting and non-interacting particles. Okay, if there are no questions, we can start discussing the ideal gas problem. Now we have an idea of classical gas, Fermi-Dirac gas, fermionic gas, and bosonic gas. We can study all three separately. And in the coming chapter in your book, the general expressions for quantum gases are obtained so that when we concentrate on fermions or bosons, we can start from those expressions. Okay? We should do that derivation now. But probably I should keep the remaining part of this lecture into discussions with you. Okay? Let's finish up at this point and start discussing.